Hey, we're still working with powers of trig functions and trying to integrate them. Here we're going to do our situation 2. We're still trying to integrate sine raised to the m power times cosine raised to the n power. And in this case we're saying n, or the cosine power, is odd. The theory here is exactly the same as situation 1, just switching the roles. So if we have an odd number of cosines, we're going to separate one cosine out. Then the remaining will be an even power, and we'll change those to a power on cosine squared. So again, looking down here, I've got cosine to the 7th. I'll pull one cosine out, leaving cosine to the 6th. Then I'll change that cosine to the 6th as cosine squared cubed. Okay, so again, the whole idea is to get a some number of square sines or cosines in this case, so that we can use Pythagorean theorem and replace cosine squared with 1 minus sine squared. And the reason for that is that if you can get both sines and cosines in there and only have one sine or one cosine left, then you can use U substitution. Okay, so let's see our examples here. I'm going to try and have some that use a little bit more U substitution. So we're going to integrate cosine cubed of 5x. Okay, so just making sure you're okay with what's happening here. So what does that mean? This is cosine 5x times cosine 5x times cosine 5x. So we'll separate one of those, so there'll be a cosine of 5x by itself times a cosine squared of 5x. And again, in this case, it's an even power. So, it's already a square, so we don't have to do as much work. But we'll rewrite that as keeping the first one cosine of 5x, and it'll be times 1 minus sine squared of 5x. Okay, so adding a little bit extra layer here. So we've done everything I've said in the steps here. The rest of it is going to be to finish out the problem with the U substitution or whatever comes up. So let's rewrite it over here. So we still got the original problem, just in a different form. So cosine of 5x times 1 minus sine squared of 5x dx. So last time we got here, we used the U substitution. We can do that again. It might seem a little bit scarier since this is not just sine of x, it's sine of 5x. But let's see here. Let's try the U substitution. Let's let U equal the sine of 5x, because we want it to be the one with the power on it. The one that we got out here all by itself, that's the one we're going to have as the du. That's supposed to be the derivative. So if U is sine of 5x, then du is 5 cosine of 5x dx. And if we isolate that, we'll have 1/5 du equal to 5, excuse me, I'm getting rid of that 5. 1/5 du equal to cosine of 5x dx. Now my s looks like a 5. So let's do a couple of substitutions here. We're going to let the cosine 5x dx be 1/5 du, and we will let sine of 5x be u. So let's rewrite our integral. I'm going to put the 1/5 out front just so it's not stuck in there. Integral of 1 minus u squared du. So let's see here if I got that right. I replaced the sine of 5x with u, and I replaced the cosine with 1/5 du. Yes, very nice, very, very nice. So what do we get here? When we integrate, we get 1/5 times u minus 1/3 u cubed. We'll distribute that 1/5. Oh, there's a plus c out here. We'll distribute that 1/5, and we'll replace our u with sine of 5x. So 1/5 sine of 5x minus 1/15 sine cubed of 5x plus c. So barring any mistakes, we have got the integral. And this will work if you have a definite integral as well. If I have endpoints, I do the same integration. I just have to plug that a and that b endpoint in at the end. So the integration process doesn't change. It just seems to get a little bit more complicated every time we introduce something new. Okay, let's do another example here. I have cosine cubed of 2x times sine squared of 2x dx. I purposefully have the same angle in here, and that's important because the formula sine to a power, cosine to a power is using the same power, the same argument. But the idea here is that if you look at this thing, the cosine part is odd. Okay, so we're going to do what we just did. We're going to rewrite it as the integral of cosine of 2x times cosine squared of 2x times sine squared of 2x dx. Okay, so with that, we're going to take the fact that we've got cosine squared here. It's already a square, so if you wanted to show that we were doing a little bit extra here, you could show that that was to the first. So we separated the powers, and then we want them in groups of squares, so there's only one group of a square there. But we will replace that, and we'll have the integral of cosine 2x times 1 minus the sine squared of 2x times the sine squared of 2x. And that's quite a bit. It's easy to make a mistake there. So let's rewrite the whole thing over here. And then we'll probably do our u substitution. So the integral of cosine of 2x times 1 minus the sine squared of 2x times the sine squared of 2x dx. And I'm going to replace that big 2 with, it looks like an actual exponent. So the idea here is there's quite a few sines, but there's only one cosine. So if all the sines become u, then there only needs to be one du, one u prime floating around. So let's see what happens if we do a u substitution. We will let u equal sine, because we want the cosine, the singular one, to be the du. So u will be the sine of 2x. Du will be 2 from the chain rule, cosine of 2x dx. So 1/2 du equals cosine 2x dx. So let's try and match some things up here. Let's find some fun new colors. Blue's not a good one. Purple. So all my sine 2x's are going to be u's, and all of my I'll use the orange. All of my cosine 2x dx is going to be 1/2 du. So I'm going to rewrite this thing. It'll be 1/2 the integral, there'll be a du out here at the end, of 1 minus u squared times u squared. So making sure we know where everything came from. The 1/2 du replaced the cosine dx, and the u replaced the sine squared 2x. Okay. So let's clean up a little bit. 1/2 can hang out front. Integral of u squared minus u to the 4th du. Yeah. Let's slide up this a little bit. And what do we got here? We'll have 1/2 times 1/3 u cubed. The nice thing is we're just doing reverse power rules. Minus 1/5 u to the 5th. This will be plus c. But let's take it back to x, which means all our u's are going to be sine 2x. So we're going to have 1/6, distributing the 1/2. So 1/6 sine cubed of 2x minus 1/10 sine to the 5th 2x plus c. Okay, so we did the exact same thing as when the sine power was odd. We just had a different substitution. Okay, so let me just make a point here without making a whole new video. Note, so if we go back to trying to integrate sine of a power times cosine to a power, if both powers are odd, it doesn't matter which method you use. So for example, if you had sine cubed times cosine cubed, you could either separate the sine or you could separate the cosine. You wouldn't want to do both. But you could use either situation 2 or situation 1. Set them backwards, but 1 or 2. And probably what you would want to do, if I'm not mistaken, is you would want to use the method with the lower odd power. So if we had a cube and a 5th power, I think you would want to use the one that goes with the cube because it would give you less work in the end. I ask you to try that out. I don't think I will work it out unless there's some problem you have. But try that out using either method just so you can get a little bit more practice. Thank you. I think I'm still recording, but I can't figure out where to stop it. So I'm done with this. Just give me a minute to figure out how to stop it. You can just hang in there until I get there. Or you can go away. It's not necessary for you to be here right now.